Swayam Prabha. Digital India. Educated India.
When we talked about the Kaya identity, one of the factors that we need to look at is what is the emission factor. So, and this is something that we can do from first principles. So, whenever we are looking at a useful energy or a useful output that is being produced, for instance, tons of steel, kilowatt hour electricity, how much electricity we are getting in a power plant. So, we would like to see, as we do that, how much is the carbon dioxide emissions. So, this will depend on the composition of the input or the fuel, the efficiency and the characteristics of the conversion device. Similar calculations instead of CO2 can be also done for SOx, particulate matter, and the methodology is the same for all pollutants. The calculations are all possible from a basic stoichiometry and an understanding of the process. So, we will take an example, the same example that we took in the last class when we talked about, in the previous lecture, we talked about a thermal power plant being rated at 500 megawatts and using coal, and we calculated how much coal and how much energy is used. So, let us just recast that question. If this thermal power plant has an efficiency of 38%, calculate the emission factor of the plant. So, the input energy used is coal with a net calorific value of 4500 kilocalories per kg, and the percentage of carbon in the coal is 50% by weight. So, let us start this calculation. So, the output is 1 kilowatt hour. 1 kilowatt hour is 1 kilojoules per second into 60 seconds per minute into 60 minutes per hour. So, we have basically this is equal to 3600 kilojoules. This is the output. For this particular output, 1 kilowatt of electricity, how much is the energy input? So, the energy input is 3600, that is the output, divided by the efficiency, which is 0.38, and if you calculate this, you will find that this comes out to be 9474 kilojoules. Now, for producing this per kilowatt hour of electricity output, how much coal am I using? So, for this I need to just divide this by the energy content in the coal. So, the coal used per kilowatt hour is 9474 divided by 4500 into, this is kilocalories per kg, into 4.18 kilojoules per kilocalorie. Okay. So, this comes out to be 9474 divided by 18,810, and if you do the number, you will find that this comes out to be 0.504 kg of coal per kilowatt hour. Okay. So, we found out how much coal is used per kilowatt hour of electricity. Now, let us calculate what is the amount of CO2. So, we also know the composition of the coal, and that composition shows that it is 50% by weight. So, is carbon. So, the kg of carbon per kilowatt hour is 0.504 into 0.5, right, and this comes to 0.252 kg of carbon per kilowatt hour. But we want to calculate how much is the CO2. So, we will assume in all these calculations, you can see in the IPCC norms, we will assume complete combustion in an ideal case. So, that means C plus O2 giving you CO2. Now, 1 kilomole of carbon will react with 1 kilomole of oxygen to give 1 kilomole of CO2. 1 mole of carbon is 12 kgs and this is 44 kgs. So, if we look at the kg of CO2 per kg of carbon, this will be 44 by 12. So, if we want to know the kg of CO2 produced per kilowatt hour, we will multiply 0.252 into 44 by 12 and this comes out to be 0.923 kg of CO2 per kilowatt hour. Now, what you could do is you can see there is a Central Electricity Authority CEA. It gives norms of CO2 emission factors for different power plants in the country. I think you will have probably 2016 data is the latest which you can get. You can look at it and you will see many of these plants are in this kind of range. So, this is something that you can calculate. Just like we have done this, we can do a similar thing for a vehicle, we can do a similar thing for an industrial process. For any place where you are doing this, you can get the emission factor. Emission factor into the activity level will give you the total emissions, sum it up over all these and you get the cumulative. So, this is a simple calculation and something that you should be able to do on your own. Please remember on the web you will find different emission factors for let us say power plants. They may be for Australian coal in Australia, they may be for European coal. The calorific value is different, the efficiencies are different. So, do not use emission factors from other contexts for your context, do the calculation yourself. Okay. If you look at the different fuels, when we looked at coal, if you look at oil or natural gas, you will see that the net calorific value is different, the percentage of carbon is different. You will find that all fuels have either have combinations of carbon and hydrogen, and natural gas has more of hydrogen content, so that on a per unit basis when we look at it, the CO2 emission factors are lower. So, this table shows you the kind of norms of emission factors, CO2 per gram, CO2 gram equivalent per kilowatt hour, and you can see that for coal you have a whole range going up, the average being of the around 0.9 to 1 kg. You can see that for natural gas it's about half that number. And when you look at renewables, you see here all the renewables are in the range of 20 to 50 grams, less than 100. And almost in some cases biomass is neutral. All of this is including the entire life cycle. So, for instance, if you look at a wind turbine, it will be the steel which is there and what has been the CO2 emissions to produce that steel. So, when we think in terms of managing the CO2, the options that we have are increase the sinks or reduce the sources. Increase the sinks means we can do afforestation. In reducing the sources, we can look at the fuel mix, changing from coal to oil to natural gas. We can look at energy efficiency, we can look at renewables, we can look at nuclear. We can also look at carbon capture and storage. And which technology we'll use depends on the kind of scale, depends on technology development, depends on cost. So, in a sense, as we go forward, we have the choices between mitigation, adaptation and suffering, and the decisions that we take today will decide the combination of this. So, either we can mitigate. If we don't mitigate and then there is some temperature rise and climate change, we need to be able to adapt, and we need to look at when that changes happen, what will we do, and if we cannot adapt or mitigate, then we suffer. So, This is a problem which is a global problem, and this is a problem which needs all countries to get together and come up with solutions. You can do as homework, you can check the IEA statistics for India for 2 years. I am suggesting 2005 and 2015. Calculate the terms of the Kaya identity for both these years and see and think how these factors can change in another 10 years or another 20 years. What are the possible future scenarios? What interventions can we make to reduce the carbon intensity? As we go along in this course and we look at economics and policies, towards the end we will discuss some of this. We will also have a recording of some of the country studies where some of our students will present some of the countries and what are they doing in terms of the Kaya identity and the policies. In Paris, we had the Paris Agreement a couple of years back, essentially where all countries got together, and in the IPCC meetings, the problem in this is that it is difficult to get a consensus. There are countries which are emitting much more than their global share, but they are also highly developed. They do not want to change their trajectory. So even to decide whether we should have an emission norm which is CO2 per person and give a right to emit which is on a per capita basis was not agreed upon. Several countries which have developed more want that CO2 emission to be based on historical numbers, want that CO2 emission to be on a per GDP basis, or so that the increased level of GDP is taken care of. However, developing countries are not willing to do this, and hence there could not be any binding mandatory agreements. Finally, what was decided was every country decided that this is a problem that we would like to tackle. So there was a process by which there were voluntary commitments made by different countries, and these were then ratified into the national commitments. In the case of India, the commitments that we have made are reducing the emissions intensity of GDP by about 1/3 of the 2005 level in 2030. We are planning to create 40% of cumulative non-fossil power by installed capacity by 2030, and we expect that we would get some finance from the International Green Climate Fund for this. We also plan to create an additional carbon sink of 2.5 to 3 billion tons of CO2 equivalent through additional tree cover and forests. So we will discuss some of this and the economics of this and in the future lectures. In this lecture, we have looked at the environment. We found that it is a key driver for future energy systems. We concluded that the existing patterns are not sustainable into the future, and we have a real problem in terms of climate change. We also have problems in terms of local emissions and urban air quality. We looked at the quantification through the Kaya identity and the emission factors. In future classes, we will explore the interaction between energy, economics and environment and carry on with the same thread. Thank you. These are some of the references.